can be described by the distance traveled between t equals 0 through t equals 5 plus the distance traveled between t equals 5 through t equals 12 seconds. And finally, we need to consider the distance traveled between t equals 12 through t equals 24 seconds. Let's start with the first distance between 0 and 5. If we evaluate our graph, we notice that we started at a position of -2, and at t equals 5 we ended at a position of 8. And so we covered 10 meters, right? Between -2 and 8, there's a span of 10 meters. In the second leg of the journey, between time equals 5 and time equals 12, let's take a look at what happens. Well, at time equals 5, we're at a location of 8 meters, and at time equals 12, we're still at that location. In other words, we haven't moved at all, and because of that, the total distance there is 0. Finally, if we explore the last leg of the journey, we started at t equals 12 with a position of 8, and we ended our journey at t equals 24 at a position of 5. So we traveled between 8 and 5 meters, and we were traveling to the left during that time. That is a total distance of 3 meters, and we note also that distance is always positive, and so our total distance equals 13 meters. Let's now determine the object's average speed. Well, we defined average speed earlier as speed with a bar on top. Of course, the bar means average, and it's defined as the distance divided by the time. We found the total distance just now as 13 meters, and of course the total time that has elapsed, if you notice, is 24 seconds. And if we enter 13 divided by 24 onto our calculator, the result turns out to equal 0.5417 meters per second. In part C, let's find the total displacement. Well, the definition for total displacement is delta x, and it just simply equals x final minus x initial. For our problem, x final is this value right here. This is the final position, right, at time equals 24, and that value equals 5. We can also note that the final position equals 5 in our position diagram. So the final position equals 5, and we started our journey over here at time 0 at a value of x equals -2. And so delta x, or the displacement for this particular problem, equals 7 meters. In part D, let's find the average velocity. Well, as we noted earlier, the average velocity equals the displacement divided by the time. In this case, the displacement was calculated to be 7 meters, and the time was 24, and so our average velocity equals 0.2917 meters per second. Finally, let's calculate the average velocity between time 0 through time 5. Now, what we've done is we redefined the final location and the final time as t equals 5 seconds. So based on that, the average velocity is still delta x divided by delta t, which we could spell out as x final minus x initial divided by the change in time. Now, x final now is the position at time equals 5 seconds. Let's see if we can identify that. So there's our graph, and at time 5 you'll note that our position equals 8. So that's x final. Our initial position corresponds to a time of 0, so that hasn't changed. At time 0, our position equals -2, right here. And of course the time now spans 0 through 5, so the time for this particular part of the problem equals 5 seconds. And so we end up with 10 in the numerator and 5 in the denominator. Our average velocity for this time frame equals 2 meters per second. We will now introduce the definition of acceleration. Average acceleration is a measure of the rate at which velocity is changing. And we're going to emphasize that word. With respect to time. So how do you know that you're accelerating while you're in your automobile? Well, the answer is you have to look at your speedometer. Now, if your speedometer is locked at 60 miles an hour, that means your velocity is not changing, and therefore your acceleration is 0. On the other hand, if the speedometer needle is moving, that means that you're experiencing acceleration. And by the way, it could be moving to the right, which is positive acceleration, or if the speedometer needle is moving to the left, that's considered negative acceleration. We want to note also that if there's no change in velocity, then the acceleration must equal 0. And as we noted earlier, for acceleration to exist, the speedometer needle must be moving. We'll emphasize that as well. Now, the symbol for average acceleration is an A, and you know what we use for signifying average, right? It's a line on top. Average acceleration, again, is symbolized with an A and a bar on top. The equation for it is the change in velocity with respect to time, which can be expanded into v final minus v initial divided by change in time. The units for acceleration are, well, let's take a look at this. Change in velocity, or velocity in general, has units of meters per second. Divided by time, time units are, of course, seconds, and if we manipulate this relationship algebraically, we end up with a unit called a meter per second squared. Or the alternate unit is the foot per second squared. Now let's introduce an example that illustrates the concept of acceleration. So in this example, we'll introduce an object that starts from rest and experiences an acceleration of 2 meters per second squared. What I'd like to do is to complete the following table. Okay, so let's construct a table. And I also have a speedometer over here, which we'll discuss in just a bit. Now, the first thing to note is that the object starts from rest, and here's the nature of the table. On the left-hand side, I'd like to indicate the time in seconds, and on the right, we'll indicate the velocity in meters per second. The object starts from rest, so that means that at time 0, it starts from rest, the velocity must be 0 as a result. Now what happens at time 1, 2, and 3? Well, at time 1, because the acceleration is 2 meters per second squared, that means that the velocity will change by 2 meters per second every second. So after 1 second elapses, that means the velocity will change from 0 to 2 meters per second. At time 2, that means that another second has gone by, and it also means because our acceleration is 2, our speed will increase by 2 meters per second from what it was earlier. So the speed here is 2. If we increase that by 2, our speed will now be 4 meters per second. And finally, at a time of 3, our speed will again increase by 2 meters per second every second, and so our speed will increase to 6 meters per second. So if we were in our automobile and we're experiencing an acceleration of 2 meters per second squared, what would the speedometer look like? Well, it'll start out at a speed of 0. And let's assume that our speedometer is measuring velocity in units of meters per second. So the velocity is in units of meters per second. Of course, in our automobile, the velocity is measured in miles per hour, but we'll allow ourselves to imagine a unit system of meters per second. So at time 0, our speed is 0, and this is where the needle would be at time 0. 1 second later, our speed will reach 2 meters per second. So again, 1 second later, our needle will be over here at 2 meters per second. And this corresponds to a time of 1 second. At a time of 2 seconds, our speed will be at a value of 4. So this is our new speedometer location. And finally, at a time of 3 seconds, our speed will be at 6 meters per second. We will now introduce the topic of motion in one dimension with constant acceleration. And we'll introduce this subject with the following assumptions. First of all of our problems will begin at a time of 0 and a position of 0. Also, as noted in our heading, the acceleration will remain constant. Okay. So with that in mind, we'll begin our exploration by noting an equation that we derived earlier, and that is acceleration, average acceleration, was defined as the change in velocity over the change in time. We can expand this further by noting that the change in velocity just equals v final minus v initial, and the change in time can be expanded as t final minus t initial. What we'll do next is introduce some substitutions. From now on, when we're dealing with one-dimensional motion with constant acceleration, t final will just be replaced by t. Whenever we see a t in our equations, it refers to the final time. We also noted that t initial is 0 because all problems start at a time of 0. V initial will just be referred to now as v at time 0 or v0, and v final will be referred to as just v. Our initial position, which is x initial, is just 0, and our x final will be now referred to as just plain old x. And the average acceleration will just be referred to as a because the acceleration is not changing. Okay, so with these substitutions, let's begin our analysis. The first thing I'll do is make substitutions into this acceleration equation. So rather than having a Vf minus Vi, Vf now is replaced by V, and V initial is now replaced by V0. Same with the time. T final, if you note, is replaced by T, and T initial has a value of 0. So with that in mind, our equation now transforms into A equals V minus V0 divided by T minus 0. We can simplify that as V minus V0 divided by T, and now we're going to solve for V. If we solve for V, the equation becomes V equals V0 plus AT. And I'd like for you to work out the algebra. If you have any issues, please raise those issues during class, and we will discuss how to resolve them. This is our first one-dimensional motion with constant acceleration equation. And again, it notes that V, which represents final velocity, equals the initial velocity plus the acceleration times time. It just so happens that when the acceleration is constant, we can remove the bar from the A because the acceleration equals the average acceleration. In other words, the acceleration remains constant at all times. Let's now recall another equation, and that is the average velocity was defined earlier as delta x over delta t, which will expand out as x final minus x initial divided by t final minus t initial. If we introduce our substitutions, x final is now replaced by x. X initial was defined as 0 because all problems start at a position of 0. The final time is noted as t and the initial time is also 0. That yields the following result. V bar equals x divided by t, and we'll solve this for x and obtain x equals v bar t. So there's the relationship between the position, average velocity, and time. Now, this equation is often abused. We have to be very careful about avoiding the abuse of this equation. This is equation number 2, and because it is so often abused, I'm going to introduce a warning sign. There it is. This is our warning. And the reason we have this warning is because sometimes students will introduce any velocity into this equation when in fact this equation will only accept average velocity. So the warning requires that we use this equation only when average velocity is known. Okay, we'll emphasize that. And again, the key term here is average velocity. Now, it turns out when an object undergoes constant acceleration, the average velocity can also be determined by calculating the average of the initial velocity and the final velocity. And so to do that, we would just add the initial plus the final velocities and divide by 2, and that will obtain the average velocity for us. That is equation number 3. What we'll do now is we'll substitute equation number 3 into equation number 2. So where I have a v bar, I'm going to put instead a v0 plus v over 2, and let's see what results. So we'll note this operation as equation 3 being substituted into equation 2, and if we do that, the equation becomes v0 plus v over 2 times t. And I hope you can see what I've just done. The equation looked like v bar t. I erased the v bar and put in its equivalent, which is v0 plus v over 2 times t. This is equation number 4. Let's bring back equation number 1 now. If you recall, equation 1 looks like this. What I'd like to do now is to solve for t in that equation. Okay, so to do that, we'll subtract v0 from both sides. On the left-hand side, that will produce v minus v0, and on the right side, we have a times t. Next, we'll divide both sides by a, and that will produce a time of v minus v0 divided by a. Next, we will take that result and substitute that into equation 4 above. So let me bring that into the view. We're now removing t and substituting instead of t its equivalent, which is v minus v0 over a. Let's make that substitution and see what happens. So with that, x will just equal v0 plus v over 2, and instead of t, we'll substitute v minus v0 divided by a. Okay, now algebraically we can isolate the 2 and the a and bring them outside of the parentheses. So the next step looks like this. We have 1 over 2a, we have v0 plus v, multiplying v minus v0. If you recall from algebra, we will have to now introduce the FOIL method. So it would be the first times first, first times last, the inner times the first term in the second parentheses, and then last times last. The result will be as follows. Now notice that I only introduced the 2 surviving terms because if you notice the v0 times negative v0 is negative v0 squared. Then we have the v0 times v. We also have a v times negative v0. Those 2 terms cancel out. And if you don't see that, please pause the video, carry out the full FOIL operation, and prove to yourself that the 2 middle terms do in fact cancel out. In the next operation, we'll multiply both sides by 2a. So we have times 2a over here and times 2a over there. And that now causes the 2a terms to cancel out. So here's what we have so far. And finally, if we solve this for v squared, we get a result of VO squared plus 2AX. We'll wrap that up in a box and call this equation number 5. Okay, one more derivation left. It starts by recalling equation 4. Equation 4 looks like this. And we'll also recall equation number 1, which looks like this. What we'll do next is we'll substitute the right-hand side of equation 1 into equation 4. So where I have a v here, I'll substitute its equivalent because v can be represented by v0 plus at. Let's see what happens. So this produces x equals, we have v0 right here. Instead of v, let's introduce v0 plus at. We have this 2 in the denominator that carries forward, and then this t also carries forward in front of the parentheses. We'll notice that we have v0 plus v0, that's 2v0. Next, we will remove this 2 and bring it to the outside, and it'll be represented by a 1/2. The next thing we'll do is we'll distribute the t into the equation. That produces 1/2 2v0t plus at squared. Next, we'll distribute the 1/2 into this equation, and here's what we get. Notice that the 2's cancel. And the final result looks like this. X equals V0t plus 1/2 AT squared. We'll wrap that up in a box as well and label this as equation number 6. And those are the 6 primary one-dimensional motion equations. And what I'd like to do next is just summarize them in a box. So equation 1 looked like this. And you know what? Let me give this a title. So these are the one-dimensional motion with constant acceleration equations. So equation 1 was V equals V0 plus AT. Equation 2 is X equals V bar T, and remember that warning that this equation comes with. Equation 3, V bar equals V0 plus V divided by 2. Equation 4 looks like this. X equals V0 plus V over 2 times T. Equation 5 is V squared equals VO squared plus 2AX. And finally, equation 6 looks like this. X equals V0t plus 1/2 AT squared. I want to mention that we're going to rely heavily on these equations, and so we're going to need to find them very quickly within our notes. So I'm going to use my blue highlighter, and if you have a highlighter, that would be great as well for you to create a box so you can easily find these equations so that we can use them readily throughout the course. We will now demonstrate the application of these equations through the following 2 examples. In our first example, we have a car starting from rest and accelerating at a rate of 5 meters per second squared. We need to determine the time required to reach a velocity of 20 meters per second. We also need to determine the car's position when its velocity equals 30 meters per second. Let's start by identifying what is known. The words starts from rest imply that the initial velocity equals 0, and in our equations the initial velocity is specified as v0. That's the velocity at time 0. So v0 in this example equals 0. Next, the problem tells us that the acceleration equals 5 meters per second squared. So A equals 5 meters per second squared. In part A, we want to find the time to reach a velocity of 20 meters per second. Now, how do we define this velocity? Clearly, we started from rest. That was our initial velocity, which is v0. Final velocity is just noted by the letter v in our equations. So v, in this case, which is final velocity, equals 20 meters per second. Now we need to find an equation that will solve for time. So let's look in our box. Now keep in mind, v0 is known, a is known, and final velocity is known. The objective now is to find an equation in this box where everything is known except for time, because we're looking for time. So let's take a look at equation number 1. Do we know v? Well, we do. Do we have a value for v0 in this example? We do. Is the acceleration given? Well, it is. So we know every one of the variables except for time. Therefore, we will use this equation to solve part A. So the equation reads as v equals v0 plus at. Let's plug in what we know. V has a value of 20. v0 has a value of 0, the acceleration equals 5, and we need to solve for t. So this is a simple equation. It just reads 20 equals 5t, and if we divide both sides by 5, we end up with a value of 4 seconds. So that's the answer to part A. Let's take a look at part B now. It reads, determine the car's position when its velocity equals 30 meters per second. Now, which variable accounts for position? Well, if you identified x, that would be correct. X accounts for position. So in part B, we're trying to find x, and there's a new final velocity defined for us as well. The new final velocity equals 30. So in part B, we want to find x when the final velocity equals 30 meters per second. So keep in mind now the acceleration throughout these problems remains constant, so we can still rely on this value for acceleration. Now, of course, when the speed changed, so does the time, and so we can't rely on the 4 seconds. At any rate, we want to find an equation that has an x in it where everything else is known. And so keep in mind, we know the final velocity and we know the acceleration. In fact, let's write those out. We still know that the acceleration equals 5 meters per second squared, and we still know that the original velocity, the initial velocity, equals 0. So with that, let's find an equation for x. Now, the first equation does not contain an x. The second equation contains an x, but do we know this thing right here, which is average velocity? The answer is no. We know initial velocity, we know final velocity, we don't know the average. So let's move on. This equation does not contain an x in it. This equation does contain x. Now let's see if we know everything else. Do we know v0? Well, the answer is yes. We also know the final velocity in part B, but we don't know the time. So this equation is not useful. Let's try equation number 5. There is an x contained within it. We do know the final velocity. We do know the initial velocity, and we do know the acceleration. This is the equation we're going to use. So the equation is v squared equals vo squared plus 2ax. Let's plug in what we know. V, which is final velocity in part B, is now 30. The initial velocity is 0. The acceleration remains constant at 5, and we're trying to determine x. So this equation, if we square the 30, we get 900 on the left. 2 times 5 is 10x. And you can see that the final position of the car, if we divide both sides by 10, turns out to equal 90 meters. Earlier, we mentioned that the one-dimensional motion equations are only valid whenever the acceleration remains constant within a problem. So how do we approach a problem where acceleration changes? It turns out that whenever acceleration changes within the problem, we have to divide the problem into distinct phases for each acceleration period. So, whenever acceleration changes within a problem, the problem must be divided into distinct parts called phases. For each period of acceleration. The phases will have a very important relationship. It turns out that they have a common thread. And that is the final velocity of a given phase will equal the initial velocity of the next phase. Stated concisely, we can write that V final in, let's say, phase A, which would be our first phase, will equal V initial of the next phase, which we typically label as phase B. And please keep in mind that V final in phase A is labeled as V, and V initial of any given phase is labeled as V0. We will now introduce an example that involves multiple phase analysis. So here's our example. It reads, a car is traveling at a rate of 35 meters per second while accelerating at a rate of 3 meters per second squared for a period of 5 seconds. At this instant, the driver notices a traffic light 246 meters ahead and immediately applies the brakes, causing the car to stop when it reaches the traffic light. We're going to determine the total distance traveled, the car's acceleration after the driver applies the brakes, the car's velocity at t equals 7 seconds, and the car's total time of travel. So the first thing to note is that the car begins traveling with an acceleration of 3, and then later in the problem, namely 5 seconds later, the driver applies the brakes, and that's going to cause a negative acceleration. The brakes will cause the car to slow down, whereas in the first 5 seconds it's speeding up with a rate of 3 meters per second squared. And so we have two phases within this problem. So we'll separate the problem into two phases, and we'll quantify our information within a chart. So our chart has a side with phase A and another side with phase B, and let's take a look at what we know about the initial stage. The car's traveling at a rate of 35 meters per second. That means initially it has speed, and we indicate speed, by the way, graphically, by introducing speed lines behind the object. It starts out at 35 meters per second. That's its initial velocity, and initial velocity is noted by V0. Next, we notice that the acceleration equals 3 meters per second squared. And the time frame equals 5 seconds for phase A. So the time equals 5 seconds. Next, the driver notices a traffic light 246 meters ahead. That's a distance of 246 meters, and distance is denoted by x within our equations. So x equals 246 meters within phase B. And the brakes apparently cause the car to stop when it reaches the traffic light. When it stops, its final velocity in phase B equals 0, and final velocity is noted as V. Let's also include this information within our diagram. Okay, so we've drawn the car at 4 distinct locations, and the first 2 images help to identify the first phase of the problem. So this is the phase where we're starting out with 35 meters per second, and we are traveling for 5 seconds. So between here and here is phase A. After 5 seconds, the car is slowing down until it reaches a full stop at the location of the traffic light. So between this location and this location, we are defining phase B. Now, let's also introduce speed lines where it's applicable. The car is definitely moving after 5 seconds when the driver starts to apply the brakes. This is the location for Part C where we're asked to determine the car's velocity at t equals 7 seconds. Certainly the car is still moving there. And over here we will not introduce speed lines because the car came to a stop. Let's now bring these known values into our diagram. V0 reflects the car's speed at the initial position, and we know that right here the initial velocity equals 35 meters per second. We also know that at this location the time equals 5 seconds. We do not know the final velocity that the car is traveling when it reaches the end of phase A. In other words, we don't know the final velocity when t equals 5, so we'll just note that as v on this side. And we'll also note that this same velocity at t equals 5 becomes the initial velocity once the car travels within phase B. So at 5 seconds, v final in phase A becomes v initial in phase B, and we will note that. So v final here equals v initial in phase B. So this is phase B, of course, and this is phase A. We also know that the distance within phase B equals 246 meters. And finally, we know that the car comes to a stop at the end of its journey, so the final velocity at this location equals 0. Alright, so let's go about solving the problem. In Part A, we want to find the total distance traveled. And in order to do that, we have to consider the distance traveled within phase A, in other words, within the first 5 seconds, and also the distance traveled within phase B. And by the way, we already know that distance. It just so happens to equal 246 meters. So in Part A, once again, we want to find the total distance. We'll call that total distance x total, and we'll note that x total equals the distance traveled in phase A plus the distance traveled in phase B. We noted that xb is already known, put a check mark there. We do need to find the distance traveled in phase A. So which equation will produce the distance traveled in phase A? Well, we'll keep in mind that we know V0, A is known, and T is known, and we'll travel now to our blue box, which is right here. And let's examine this equation. Well, this equation doesn't have an x in it. This one, well, we don't have the average velocity. This equation does not contain an x. This one does. Let's see if we can use it. Well, we have v0. The problem here is we don't know the final velocity in phase A. How about this equation? Again, same problem. We don't know the final velocity in phase A. Let's see equation number 6. It reads x equals VOT. We have VO, we have the time, and we also have the acceleration. This is the equation we're going to use. So it reads x equals VOT plus 1/2 AT squared. Our initial velocity from the table is 35. The time is 5 seconds. The acceleration is 3. And the time, again, is 5 seconds. So if we work this through carefully, our calculator will produce a value of 212.5 meters. Let's note that this work was conducted in phase A. And so this, of course, is just XA. And to calculate X total, we can just rely on this equation above. We have the value for XA. It equals 212.5. The distance traveled in phase B is located right here, 246 meters. And if we add those up, it turns out that the total distance equals 458.5 meters. Now in part B, we want to determine the car's acceleration in phase B, or after the driver applies the brakes. And clearly, once the brakes are applied, we are within phase B, and I'll note that. Okay, now in order to find the acceleration, or in order to find just about any variable, we need to have at least 3 quantities known within our table. And unfortunately, if you're looking at phase B, we only have access to 2 values. So let's note this limitation that we're dealing with right now. So again, in order to proceed, in phase B, at least 3 quantities must be known. In other words, if you try to find an equation for acceleration within our 1D motion box, you will be unable to solve for acceleration because you only have 2 variables known. So the question is, how do we now obtain a 3rd variable within phase B? And the answer to that is to take advantage of the fact that the final velocity in phase A could be used as the initial velocity in phase B. So what we'll do is we'll go back into phase A and solve for the final velocity within phase A, which we can do because we have 3 known variables within phase A. So let's enter phase A. And we'll find V first. Now keep in mind, within phase A, we know V0, we know A, and we know T. And let's now go to our 1D equation motion box and see if we can find an equation for V. So here's our box, and let's examine equation number 1. It has a V in it, We also know V0 in phase A. We know the acceleration and we know the time. This is the equation we're going to use. So the equation is V equals V0 plus AT. V0 is known to be right here in our table as 35. The acceleration is 3 and the time is 5. So again, V0 is 35, the acceleration is 3, the time is 5, and we obtain a value of 50 meters per second. And this, of course, is the velocity in phase A at the end of the time period. In other words, at t equals 5. We can use that as the initial velocity in phase B. So I'll make a note to that effect. This equals V0 in phase B. So now let's analyze phase B. Now what are we looking for in phase B? We're looking for the acceleration, and we now have knowledge of the initial velocity in phase B, which is 50. What I'll do now is I'll bring this value into our table. And I'll separate what we knew earlier from what we know now with this red line. So right now we know that V initial in phase B equals 50 meters per second. We also know that V final in phase A was 50 meters per second. And of course this value of V transfers into the phase B box as the initial velocity. So this is a good way of organizing our information. Now that we have 3 known quantities, how do we go about solving for the acceleration? So again, we know x, we know the value for v, we know the value for v0. Let's go to our 1D motion equation box. Alright, so here's our box, and let's see if the first equation will solve for acceleration. And if you examine this, you notice that it won't do the job because we don't know the amount of time that we're spending in phase B. The next equation that contains acceleration is this one, and let's see. We do know the final velocity in phase B, it's 0. We do know the initial velocity in phase B, we just found it, and we do know the distance traveled in phase B. This is the equation that we'll be using. Alright, so let's write it. It reads as v squared equals v0 squared plus 2ax. We know that the final velocity is 0. The initial velocity we just calculated is 50. The acceleration is unknown, and the distance in phase B is 246 meters. And so we obtain 0 equals 2,500 plus 492a. We'll transfer the 2,500 to the other side, and that produces negative 2,500 equals 492a. Next, we'll divide both sides by 492, and the result becomes negative 5.081. And the units for acceleration, of course, are meters per second squared. Now, the negative right here signifies that the car is slowing down. We have a positive velocity and a negative acceleration. That means that the acceleration is slowing down the car. It's really a deceleration. So again, this negative means the car is slowing down. Let's also bring this value into our chart as well under phase B. So we just found out that the acceleration in phase B equals negative 5.081 meters per second squared. And again, this line tells us that these values were obtained after the fact. whereas the values above the line were given to us at the beginning of the problem. Okay, so in part C, we would like to determine the car's velocity at t equals 7 seconds. Now that's the time from the beginning of the problem. And we'll also note that at t equals 7, the car is in phase B because we're only spending the first 5 seconds in phase A. So here's our diagram, and this is a good time to note that the time for the car's location, which is right here, is 7 seconds. But that's the total time. If we're going into phase B, we need to apply the time that we're spending only within phase B. So if we just do a simple subtraction of 7 minus the first 5 seconds, we'll note that the time that is useful within the equations is actually 2 seconds. Okay? The time that we're spending in phase B is actually 2 seconds between this starting point and this final point. Now that's not the total time, but when we're asked to find the velocity of the car at t equals 7, we have to use t equals 2 within our equations and within phase B. Let's just refresh what we know. So we are now in phase B, and here's what's known. For this particular part of the problem, we know that the time equals 2 seconds, right? 7 seconds means we're 2 seconds into phase B. We also know that we started within phase B with a velocity of 50 meters per second. And we also know the acceleration equals negative 5.081 meters per second squared. With that knowledge, let's now take a look at our blue box 1D motion equations and see if we can find an equation that solves for the car's velocity. Alright, so here's the box of equations, and the first equation has v in it, and we also know that v0 equals 50, the acceleration equals negative 5.081, and the time we determined equals 2 seconds. This is the equation that we'll be using. Okay, so v equals v0 plus at. Again, v0 equals 50. The acceleration is negative 5.081. And the time equals 2. And if we solve that with our calculator, the value equals 39.84 meters per second. In part D, we're asked to find the total time of travel. We'll just label it as T total. And again, whenever you have multi-phase problems, in order to determine the total time, we have to look at the time spent in each of the phases, or total distance, again, is a matter of evaluating the distance spent in each of the phases. So T total will just equal the time we spent in phase A plus the time we spent in phase B. And note that we already know the amount of time that we spent in phase A, right? If we're looking at our phase A box, that information was given at the beginning of the problem. The time equals 5 seconds. So we'll place a check mark on top of TA. However, we do not know how much time we spent in phase B, and so we need to determine that. Alright, there's plenty of information available within phase B right now, so let's just go right to phase B. We'll take inventory of what we know. And we know a lot. Here it is. We know the distance, we know the final velocity, we know the initial velocity, we know the acceleration, we know a lot of information. Let's now go to our equation box right here. And let's see if the first equation is useful. We're trying to solve for time. We know the final velocity is 0 in phase B. We know the initial velocity is 50. We also know the acceleration. This is the equation that we'll be using. So the equation once again is V equals V0 plus AT. We have 0 equals 50 plus the acceleration is negative 5.081 times t. In order to solve this, we'll bring this term to the left-hand side, and algebraically, the sign will change. Remember, whenever you transfer a term to the opposite side, the sign will change. So we have 5.081 t equals 50, and the time equals 9.841 seconds. Of course, to obtain this time, we divide both sides by 5.081. Now, keep in mind that this is just the time that we're spending in phase B. In order to calculate t total, we'll just note the earlier equation, which is TA plus TB. We spent 5 seconds in phase A. We spent 9.841 seconds in phase B. So the total time of this journey equals 14.84 seconds. And that concludes this lecture.